Assalamu alaikum. In this series, Mr. Omar will guide you through some practice problems to cover all items included in the coverage issued by Emirate Schools Establishment, E.S.E. This is part 5. Have a fruitful time.
السلام عليكم ورحمة الله وبركاته. Welcome back. Bismillah ar-Rahman ar-Rahim. Now, goal number 14. I have many questions for this goal as mentioned in the coverage. First one is about spring. Spring has a length of 15.4 centimeters. This is the length of the spring, this is the initial length, and it should be converted into meter by multiplying times 2, and is hanging vertically from a support point above it. A weight with a mass, this is a mass, is attached to the spring, causing length to extend to a length of, this is the final length. What is the value of the spring constant? Now, first of all, find the extension. Which is x. The final length minus the initial. 28.6 minus 15.4. 28.6 minus 15.4 is 13.2. But don't forget it is centimeter, so 13.2 times 10 to the minus 2 centimeter. Now, the force is the weight of the mass. Which is Fg, m times g. How much m? Is 0.2 times g 9.8. The answer will be 1.96. Now, for the time constant, we know that F equals Kx or K equals F of x, or you can use this triangle. K times x equals F. So K equals F over x. The force is 1.96, sorry. X is 13.2 times 10 to the minus 2. And the answer will be 14.8. The unit is very important. Meter per meter. How much force is needed to hold the weight at the position 4 cm above minus 28.6? Now we need to push it up a little bit. So the force needed equal the initial force minus the final force. The initial force is Kx final minus Kx initial, and we need the magnitude, so I'm pressing absolute value. K final minus This x final minus x initial is nothing but 4.6 centimeters because the spring was at this position. This is 28.6, and we need to make it higher by 4.6. So this is the delta x. And we have k from the previous one, 14.8, times the distance, 4.6 times 10 to the minus 2 to be in 14.8 times 4.6 e to the minus 6.6808. Now spring start motion, okay. A massless spring located on a smooth horizontal surface. Horizontal, that means change in the potential energy equals 0. Is compressed by a force of, this is the force of compression, which results a displacement of, this is x, the extension, and should be converted into meter. Multiply by 10 to the minus 2 meters. From initial equilibrium position as shown. A steel ball of mass is then placed in front of the spring. What is the speed of the steel ball when it is shot off by the spring? Okay. Now, for the extension with the force, we can find the spring constant. F equals kx. So k equals F over x. We have F and we have x. Leave it like this. Now, using the conservation of energy, change in the kinetic energy of the ball, the change in the potential energy of the ball is equal to the external work. The only thing that does a work on the spring and the ball is the spring. The work of the spring plus or minus 1/2 k x squared. We use the plus sign if the spring start the motion. And we use the -1 if the spring opposes the motion. Or stop the motion. In our case, the spring pushes the ball so it starts the motion. So put here 1/2 k x squared with a positive sign. And as we mentioned before, delta U equals. What is delta k? It is 1/2 m v squared final minus v initial squared. The ball is at rest initially, and we can cancel the 1/2 factor. Then m v squared equals k x squared, which leaves us with v squared equals k x squared over the mass. And if you take the square root, you will get v immediately. Now, I want to substitute 4k from here. Is F over x times x square over m. Now cancel x with x and you are left with fx over m. Now substitute. The force is 63.5. The extension is 4.35 centimeter. 4.35 centimeter. Convert into meter. Multiplied by minus 2. So now it's meter. The mass of the ball is 0.075. Yes, 0.07. Do the calculation and give my answer. The answer is 6.07 meter per second, and that's it. Now, an ideal spring has the spring constant K equals 440 Newton per meter. Calculate the distance this spring must be stretched from equilibrium for 25 joule of work. The work, as we mentioned before, is 1/2 kx squared for the spring. I need the distance, which is x. So 2w over k equals x squared. I multiply both sides by 1/2 or 2 over k. 2 over k. Two w over k. Now 2 with half, k with k, and you are left with x. So now x equals square root of 2 work over k. Substitute. The work is 25, so 2 times 25 over k, it is 440. So 2 times 25 over 440 is 0.337 meter or 33.7 centimeters. A spring is stretched 5 centimeters, so this is x, and you must multiply by 10 to the minus 2 to convert it to meter. From its equilibrium position, if this stretching requires this work, how much is the spring constant? Work 1k x squared. I need k, so k equals 2w over x squared. Multiply both sides by 2 over x. Now substitute 2. The work is 30 joule. X it is 5 centimeters. 5 minus 2. But that is square, right? Then the answer is 24,000 Newton per meter or 24 kilonewton per meter. A spring with spring constant K is initially compressed at a distance x naught from its equilibrium length. After returning to its equilibrium position, the spring is then stretched a distance of x0 from its equilibrium position. What is the ratio of the work that needs to be done on the spring on the stretching or the work done in compression? The work for the spring equals 1/2 x squared. Now the work while stretching equals 1/2 and it is positive because stretching, this is the initial, here we have increasing, while compression means negative displacement. So for compression, we have 1/2 k minus x naught squared, which is the same. So the ratio between the two works is 1. Work while stretching over the work while compressing is equal 1 divided by the two sides. Now a spring with a spring constant 238.5 is compressed by this distance. Then a steel ball is bearing of mass is put against the end of the spring and the spring is released. What is the speed of the ball bearing right after the contact with the spring? It is the same as the one before. Delta K plus delta U equals W external, which is 1/2 k x squared, and delta U, if it is horizontally, so it is 0, and we have here 1/2 m v final squared minus v initial. Cancel 1/2 with 1/2. V naught is 0. Again, V final equals k x squared over m and take the square root of k 238.5 x is 0.231 squared over the mass of the ball bearing is 0.041 So the answer would be 17.6 meter per second. Now question number 15. In a sport of weightlifting, the task is to pick up a very large mass, lift it over your head and hold it there at a rest for a moment. This action is an example of doing work by lifting and lowering a mass. Now, German lifter Ronnie Waller won the silver medal at the Olympic Games in Sydney, Australia. He lifted 257.5 kilograms in the clean and jerk competition. Assume he lifted the mass to a height of 1.83 and held it there. What is the work he did in this process? we insist on the conservation of energy. Now, for the mass, it was at rest, then it become again at rest on over his head. So delta K equals 0. Now delta U, it is mg delta H equals the work. So the work easily, it is m, which is 257.5 times G 9.8 times H 1.83. Delta H equal H final minus H initial 1.83. It is initially at the ground, so H initial is 0 because it's at the ground level. So delta H is equal 1.8. That's it. So 257.5 multiplied by 9.8 multiplied by 1.83. The answer is 4,618 joule. Once Fuller successfully completed the lift and was holding the mass without stretching arms above his head, what was the work done by him in lowering the weight slowly with negligible kinetic energy? Now, when he is lowering the lift, he will do a work with a negative sign. Why? Because his force is upward and the motion is downward, and it will be equal exactly the same as this one, but with a minus sign. So the work delta K plus delta U equals the work, the same equation. Now lifting with constant speed, so delta K equals 0. Delta U mg delta H equals work external. Now what is delta H? It is H initial minus H final. H initial is 1.83. Sorry, delta H final minus H initial. Final minus initial. Sorry again, final minus initial. Final 0 because it comes downward into the ground, minus 1.83. So M, it is 257.5, G 9.8, delta H now it is minus 1.83 equal the work. So the work is the same as before but with minus sign. Work equal 4618 with minus sign. A hammerhead of mass 2 kg is allowed to fall into a Nile from a height of, this is H initial, so H final will be considered as 0. Calculate the maximum amount of work it could be done on the Nile. Delta K plus delta U equals now delta K 1/2 M V final squared minus V initial squared plus delta U mg H final minus H initial equals the work done. Now, because it's fall from rest, So V initial equals 0, and after collision with the nail, V final is 0. So delta kinetic energy 0. If the work is needed to be a maximum, but if the work is not maximum, we have some amount of the kinetic energy. So here all the potential energy is converted to work, and because of that we say that this work is a maximum. So now W maximum equals, substitute for M to G 9.8, H final reaches the level ground 0 minus H initial, it is 0.4 meter. 2 times 9.8 times 0.4 with a minus sign is minus 7.84 joule. This is the maximum work could be done on the nail if the change in the kinetic energy is said to be 0. Let us finish this part by this question. How much work is done against gravity in lifting 6 kilogram weight through a distance of 20 centimeters? So this is the mass should be lifted, and here is delta H, and since it is up, it should be positive, and convert it into meter. Delta K plus delta U equals W external. Now the lifting is with constant speed. Just that. Delta U mg delta H equal the work. M it is 6, G 9.8, and delta H it is 0.2. H 20 centimeter minus 2 meter, which is 0.2, equal the work. So the work easily can be shown here. 11.76 joule. If you take 3 digits, 3 significant figures, is 11.8. That's it for this part. See you next part. Bye. Assalamu alaikum.
I hope that this video has enriched you more. In the description box below, there are links to both a PDF document for answers and the other videos in this series. This is the end of part 5. See you in part 6. Salam.